Harnessing solar energy offers a remarkable opportunity to embrace a renewable and eco-friendly source of power. By installing solar panels, you take a significant step towards achieving energy independence and securing a brighter, sustainable future. As the sun's rates remain constant, you can relish the benefits of inexpensive electricity for years to come. To maintain the efficiency of your solar cells, occasional cleaning becomes essential. However, manual cleaning methods may pose risks to employees, solar panel damage, or inadequate cleaning. Embrace innovative cleaning solutions and professional services to ensure maximum sunlight absorption, safeguarding your investment in the environment. As a solution, we proposed an autonomous solar panel cleaning robot. It incorporates 6 ultrasonic sensors for edge detection. 2 Raspberry Pi 3B Plus boards are used, one for vision-based operations and the other for main control tasks. Line detection and line following are achieved with a Raspberry Pi camera module. The robot features a mechanical roller brush and separate motor controller for cleaning. Tracked wheel motors are controlled by a bidirectional motor controller powered by a 24-volt battery pack. An EMU sensor measures the robot's tilt angle, and a mobile app allows manual commands and user control. The autonomous navigation of the solar panel cleaning robot relies on the white lines present on the panel's surface. The process involves filtering the raw image using Gaussian filtering, and transforming it using lab color space. After thresholding, contour area filtering is applied. This filtered image is then used for line detection, counting, and following algorithms. Additionally, an initial measurement unit is utilized to estimate the robot's orientation and tilt angle. For this purpose, 3 parallel column filters are implemented to estimate each column of the rotation matrix, representing different states of the system. Communicating between the main Raspberry Pi and the mobile app posed a significant challenge. To overcome this, we devised a solution using tunneling software. Running the robot operating system server creates a local host, and the tunneling software assigns a public IP address to it. The mobile app then connects with this public IP address. As ROS packages use ROS message type data and the app uses JSON objects, the ROS bridge server facilitated seamless two-way communication between them. Let's watch a demonstration video of our semi-autonomous robot, in different test environments.